right, 2 more lessons and then we're done with volume. Today we're going to talk about SPAV. SPAV is a shortcut or a tool to help us compare the side length and perimeter ratio of an object with the area ratio of one of the faces with the volume ratio of a three-dimensional shape. And I'm going to show you how to bounce back and forth between one-dimensional, two-dimensional, and three-dimensional calculations quickly. So take a couple of minutes, 3 minutes, maybe less, depending on what you need. Answer these first set of questions. Pause the video, answer the questions, then hit play, and we'll talk about what's going on. Okay, so we have two rectangles, one created by a dilation of the other. Our original pre-image has an area of 8, base times height, it's a rectangle, and then the image has an area of 128, base times height because it's a rectangle. And then the ratio of the sides, the similarity ratio is the ratio of the sides. That's the one-dimensional comparison between the two shapes. So we can use the height of 2 to 8, or we can use the length of 4 to 16. But either way, when we write the ratio, it'll reduce down to 1/4. So that means we used a scale factor of 4 to create the image from the pre-image. Now, if you look at the areas, the area of the original pre-image is 8, but the area of the image is 128. That is not 4 times greater. If you look at that, that's a ratio of 1 to 16, not 1 to 4. So the scale factor that was used to generate S prime, P prime, A prime, V prime for the side lengths with a scale factor of 4, but the scale factor for the areas was a scale factor of 16. That means you have to take the ratio of the side lengths and square it to figure out what will be the ratio of the areas. Now, if you think about dimensional analysis, this makes sense. Side lengths are one-dimensional measurements, lengths. Area is a two-dimensional measurement. That's why we say when we do area calculations, square feet, two-dimensional. Square meters, two-dimensional. Square inches, two-dimensional. So we square the one-dimensional comparison in order to get to the two-dimensional calculation. So for a one-dimensional measurement, length or perimeter, we have to square that in order to get to the two-dimensional comparison for the areas. Applying that to the third dimension of volume, we would take the one-dimensional measurement, length or perimeter, and cube it in order to get to the three-dimensional measurement of volume. Now, when we do some of these examples coming up, we're going to start sometimes with the one-dimensional, sometimes with the two-dimensional, sometimes with the three-dimensional calculation or measurements. No matter which one we start with, we have to get it to the one-dimensional scale factor first before we can jump to any of the other ones. So let me show you what I mean by that. One-dimensional calculation would be perimeter, radius length, circumference, side length, height. Those are all lengths. Anything that's area, lateral area, surface area, just area of a side, that's two-dimensional, and volume is three-dimensional. If we have a scale factor of 6, we would take that, square it, and figure out that the new area would be 36 times greater than the original. The reason why it's 36 times greater is because if you think about a rectangle, we would increase the length 6 times greater and the width 6 times greater. Length times width, 6 times 6 makes the area 36 times bigger. And similar with the volume, we would increase each dimension, length, width, and height, by multiplying times 6. So 6 cubed would make the volume 216 times larger than the original. The second one here, we're starting with the area ratio. Now, this is a two-dimensional ratio, and I said on the end of the previous slide, we always have to get to the one-dimensional ratio from wherever we're starting from. So, to get from a two-dimensional ratio to a one-dimensional ratio, we are going to square root. So, if I square root the ratio of 4 to 25, I get to a side ratio of 2 to 5. Once I have the one-dimensional ratio, I can take that and cube it in order to get the three-dimensional or the volume ratio. So that means for this particular shape, if the area of the bases were in the ratio of 4 to 25, then the area of the volumes of the shape would be 8 to 125. All right. Now let's go backwards from starting with the volume. If we were given the volume first, that's a three-dimensional measurement. We have to get to the one-dimensional calculation first. So how do we uncube something? So we would cube root. Now, on your calculator, you guys, most of you have graphing calculators. There is a cube root button on your calculator, a cube root function on your calculator. And I'm going to show you where that is. If you go to the math button, option 4 is the cube root. Okay? So if you do math and then option 4, you can do the cube root of 729. It'll tell you that it's 9. That means 9 times 9 times 9 is 729. So there's your cube root button. So if I do the cube root of 64 and the cube root of 343, I'll get our one-dimensional side ratio of 4 to 7. We'll square those to get our two-dimensional area ratio of 16 to 49. That's how it works. Let's do some examples. So, explain why the two cylinders are similar and find the similarity ratios of their sides, areas, and volumes. The reason why these two shapes are similar is because the ratio of the heights, which would reduce to 6 to 5, equals the ratio of the radius lengths, the radii, which is 6 to 5. That means they are similar. So the ratio of our sides, the one-dimensional comparison, would be the 6 to 5. The ratio of the areas, the two-dimensional comparison, the area of the base, we would square that to get 36 to 25. And then the ratio of the volumes of the two cylinders we see, we would cube that one-dimensional ratio to get 216 to 125. So pause it, do question 2, and then come back and check your answers. So hopefully you got 5 to 7 for the one-dimensional or the perimeter ratio, 25 to 49 for the two-dimensional or area ratio, and then 125 to 343 for the three-dimensional or volume ratio. Now I want to show you where the SPAV comes into play. So the whole idea behind SPAV is a way to organize the material that I basically just talked about in the table. So this question gives us two similar tetrahedrons, which is a triangular prism, triangular pyramid. It gives us the ratio of these surface areas. Now it doesn't matter if it's surface area, lateral area, area of one side. Area is two-dimensional. That's the A part of SPAV. The S stands for the side lengths or the similarity ratio. The P would be perimeter. Both of those are one-dimensional. The A is the area, V is the volume. We are starting with the two-dimensional comparison, two-dimensional ratio, 45 to 80. The first thing you want to do, if you do not recognize these as perfect squares, what you're going to do is reduce the fraction first. They should reduce down to something that looks like perfect squares. Then we can take the square roots of those to get our one-dimensional comparison, and then that one-dimensional comparison we can then cube to get the comparison of our volumes. Once we have the volume ratio, we can set up a proportion. Smaller volume over larger volume equals smaller volume over larger volume. Just have to read carefully to make sure we know where the 600 goes. And then you cross multiply and get your answer. All right, so if you think you're good, practice some more on your own. If you want, keep watching, and we'll get through these quickly. Number 4, we are starting with the volumes. So again, you can try to cube root these. If they are perfect cubes, then we're all set. If they are not perfect cubes, you want to reduce the fraction first. So I cube rooted them and found out that the similarity ratio, or the ratio of the perimeters, the one-dimensional ratio, is 11 to 14. We are asked to find the ratio of their heights and the ratio of their surface areas. So we already have the ratio of their heights because the height is a one-dimensional measurement. That's the 11 to 14. The ratio of their surface areas is when we square that value and get 121 over 196. That's your answer. Those are your answers. If we are given the ratio of the sides to start with, then all we need to do is square that for the ratio of the areas, and then cube that for the ratio of the volumes, and then use whatever we need to answer the question. In this case, we're given the volume of the smaller cylinder, so we set up the proportion accordingly, cross multiply, and check your answer. Okay, number 6. This one's in a different color because it's a little bit different. So let me explain number 6. A rectangle has dimensions that's 8 centimeters wide, 6 centimeters tall. Area would be 6 times 8 or 48. The rectangle is scaled horizontally by a scale factor of 2, but vertically by a scale factor of 4. That means they are not increasing the two dimensions by the same scale factor. So let's figure out the new dimensions. So it was 8 centimeters wide times the scale factor of 2 means the new dimensions would be 16 centimeters wide. And then 6 centimeters tall times the scale factor of 4 makes it now 24 centimeters tall. These shapes are not similar, but we do know the scale factors that were used to increase each of the side lengths. The new area, base times height, 384 square centimeters. How does this new area compare to the original area? How many times larger did it become? And how does the change in the area relate to the scale factors that we used up in part I? Well, if we look at image divided by pre-image, that's the area of 384 divided by the area of the pre-image of 48. What we see is that the area became 8 times greater, which just so happens to be the product of the two scale factors we used. So that means if the shape is not similar and I use different scale factors for different directions, just multiply the scale factors together to figure out the change in the area. If it's three-dimensional, you would multiply the 3 different scale factors together to get the change in the volume. So if an original triangle was scaled horizontally by 6 and vertically by 1/2, then what we would do is multiply the 6 times 1/2, and we now know our new area will be 3 times greater than the original. If our original area was 48, which it was, then the new area is 144. So a nice example of that to round this off. Last summer, I made kites for my kids. The first kite that I made had an area of 3 square feet. I decided to make the second kite a lot bigger by doubling the length of the longer diagonal, but tripling the length of the shorter diagonal. So let's figure out the area of the new kite. Well, the original kite we know had an area of 3. The product of the two scale factors, doubling in one direction, tripling in the other direction, means that the new kite has an area 6 times greater than the original. So the new kite had an area of 18 square feet. All right, just over 12 minutes, so we're doing great. Miss you guys, and we'll talk to you later.